What is going on, guys? Welcome back to another video. In this one, we will be doing a Kaggle challenge, and one of the most popular, I guess, challenges because it had the sort of most amount of teams in this challenge. And the solution that we will eventually come up with is one that scores in the top 1%. So it's a pretty good solution, and it's pretty simple, right? I tried to make it as simple as possible. So first of all, let's just take a look at this challenge, because this was actually a pretty special challenge, I think, because so the idea is to sort of predict, I guess, if a customer made a transaction or not based on some features. And so if we take a look at the data, what's really weird about it is that the data is anonymous. So we only have sort of a value. Let's see on the training data. We only have a sort of a target, 0 or 1, so it's binary. And then we have some variables, and we have 200 variables. We don't know what any of the variables mean, and so pretty much it's just a black box that we don't know anything about, which makes feature engineering pretty difficult. But nonetheless, we're going to see how to do that and how it will help. But what I want to start with actually is just to sort of create a baseline, right? I think that's a good starting point. Just create some simple, in this case, we're going to create a simple neural network. We're going to see what that baseline is, and then all the sort of things we'll try out will be to improve that baseline. All right, so what I want to do is take that data, and so just go down here, download the data. All right, so I've downloaded the data. We have a training set which has 200,000 examples, 200 features of each example, and similarly for the test set. So we're not going to do much sort of data analysis of this. So I want to just create a Jupyter notebook, and here is where we will get data. So we'll be doing some feature engineering and stuff like that later on. But for now, we're just gonna not do much. Let's see if I can make that a little bit bigger. So for now, maybe we just want to do read CSV of train.csv. Just make sure that it looks all right. And then we can do maybe just show 5 examples so we can just see how they look like. All right, so here we go. We have one column ID code, which is the example of that one. We have the target, and then we have all the variables for that one. All right. So what I want to do is sort of when we create the data later on, all of that stuff is going to be in Jupyter Notebook, and then we'll create the model and so on in PyCharm. All right. So make this full screen, and I guess what we're going to do is we're going to have a dataset file, and we're going to have one train. And we're going to have a utils file. All right, so what I want to do now is nothing special at all. I just want to create a baseline that I can measure against later on. So we might start off with the data set. So we're going to import pandas as PD. We're going to actually import torch. And to create a data set, we're going to use something called tensor data set. So we don't have to create a custom class and so on. It's going to make it a lot simpler. So from torch utils.data, import tensor dataset, and we're also going to need a random split. So from torch.utils.data.dataset, import random split. All right, and we'll just create a function getData, and all we're going to do here is load the training data. So train data. And we'll load that with pandas. So pd.read CSV of train.csv. And those 2 columns of the ID code and the target, we obviously don't want that for the features, right? So we can do y is train data of target. And then for the sort of training data, we can do train data.drop. And we can specify the ID code and the target, and those are going to be the columns, so axis 1, and that's it. So now that we have those, we want to actually convert those to tensors. So we'll do xTensor is torch.tensor of x.values, and we'll do dtype is torch.float32. I think it's float 64 by default, but you know, we don't need that good precision, so we'll just convert it to float32. yTensor is y.values, and so you know, now we read the entire training data. Obviously, we want a validation data as well, otherwise it would be kind of useless. So we'll just do dataset is tensor dataset of xTensor and yTensor. And if you're not familiar with tensor dataset, I wasn't actually before I did this competition, but yeah, it's actually pretty nice, especially if you work with small data sets like this one. You can just, or it's not small, but you can read the entire thing into memory, and then you can just do tensor data sets of those two tensors, and it's going to automatically create a torch data set for you. And then you can you know, do train ds, val ds is random split of that data set, and then we specify the split. So in this case, we'll do int 0.8 times the length of data set. And we can also, from math, import seal, and then we can do, I think this should work, because we want to have all of the examples, and then we want to do seal of 0.2 times length of data set. That should work, I think. So, you know, we want 20% on the validation data, 80% on the training data. And so why not do the same thing? We can just copy that code, and we'll do the same thing for the test set. So I guess we need to also load that first. So test data is pd.read csv of test. And let's see, what do we need to change? So obviously there are no targets, right? So we just have X, so we can't drop target. But everything else here should be okay. We'll just change this to test data set, and we can remove that thing. Yeah, I actually also know that we need to have test IDs for when we do the submission later on. So we'll get those as well. So we'll get test data of ID code. I think that's it. Yeah. So, you know, the submission file is going to be, you know, the ID, comma, the predicted probability, right? So that's what we will create a CSV file for the submission later on. But now we'll just return train data set, val data set, test data set, and then test IDs. All right, so nothing, you know, fancy here. We just created a way to load the data. Now that we have that, we can create the train function. And I'm going to copy paste the imports because I think, you know, we can just save some time that way. So we're going to use torch. We're going to, from sklearn, we're going to import metrics. And that's why, because we want to use ROC instead of just accuracy. And we can use sklearn for that. And then we're going to import tqdm for progress bar, torch nn, torch optin. And this one we're going to need later on. From dataset, import get data, and then we're going to have data loader. All right, so maybe we can just set, you know, device CUDA if torch.CUDA is available, otherwise CPU. What else? So we're going to create a network, right? Class neural network, inherit from NN module, create init method. Maybe we can send in some input size. Yeah, let's do that. And then we can do super nn self.init. And I guess we can just do very, very simple neural network. So let's do self.net is nn.linear of, oh, sorry, not nn linear, nn sequential of nn linear of input size to, maybe we can do 50, and then nn.relu in place equals true. And then we can do nn linear 50 to what is it? Just a single one. So single output for the prediction. And I guess also what we need to do, in fact, is create a, so I guess what you would do is you would normalize the data, right? By subtracting the mean and dividing by the standard deviation. I'm going to do this, which is not good to do. Well, I'm going to replace that with a batch norm 1D. So I'm just going to normalize it with a batch norm at the start, which is, this is computationally, unnecessary. You can normalize it first, but whatever. We can afford that, I think. And then in the forward, we're going to send in x and just return self.net of x. Right? We're really not doing anything fancy for our first neural network, right? We just want to create a baseline that we can then sort of make improvements on. So our model is going to be, let's see, nn of input size equals 200. And we'll also create the sort of the loading of the data, right? We have the training data set, val data set, test data set, and the test IDs from get data, but we want to create a data loader of those, right? So we'll do train loader is data loader of train data set, and we'll specify batch size, so 1024. And this is something, this is a hyperparameter, and then we'll do validation loader, test loader, test data set, test data set. For the validation, we'll just do validation data set. And yeah, we can also do, shuffle equals true here. All right. So let's see, what we want to do now is maybe just check that it works. So for xy in train, actually we can do xy is next of iter of train loader, print x.shape, right? So let's run it. Yeah, and this takes a while actually, because we have pretty large CSV file, but hopefully it doesn't take too long. Yeah, all right, so that seems to work. We have 200 features, we have 1024 batches, perfect. So let's continue on creating all the stuff that we need. So we need to have an optimizer, right? Optimizer, we're going to use Atom. We'll send in model.parameters, learning rate, we'll set to, let's see, 2e minus 3. And, you can do a grid search and try to find good values here. And then weight decay 1e minus 4. The loss function we're going to use is nn.bce loss. Okay, so for the loss function, since it is binary, we're going to use binary cross entropy, but you have pretty much two options here. You can use BCE loss, which means that you've already outputted a sigmoid, or you can use, or rather, the output has gone through a sigmoid before you send it to BCE loss. Otherwise, you use BCE with logit loss, and then it will run a sigmoid inside that loss function. So I'm going to use BCE loss here, and I think I'm just going to do return a torch.sigmoid of that, like that. And then we can do, yeah, BCE loss, that looks good. All right, so let's do for epoch in range of 20 maybe. We can do for batch index, comma data, comma target in train loader. And we'll just set up the normal stuff. We'll set it to device, targets to device, and then forward, we'll just do scores is model of data, and let's just print scores dot shape like that, and then we can do continue on. So we'll do loss function is the loss function of the scores and then the targets. Optimizer, you know, .0 grad. All right. Oh yeah, so we need to have enumerate. Loss.backward, right? So we zero the gradients, we do loss.backward, and then optimizer.step. All right. Okay. Yeah, so we need to also do the model.toDevice. And now that should be all, I think. And we can just, I guess, print the loss function and just make sure that our network works, first of all. So a perfect way to do that is by just getting one batch, all right? Always get one batch before you do anything else. And one thing we can do here also is do that view of -1. So just flatten everything. So what you do for a batch first is that you just do data.targets is next of iter of train loader, right? This is going to save you so much time. It's kind of just something that's kind of boring to do, but you should always do this. And you should just print the loss, or, you know, if you have accuracy, that's even better. We haven't implemented accuracy, but what I want to see is just that the loss decreases, and then I know, you know, that, you know, it works. And yeah, we'll run it for some more epochs, maybe 500. And you know, I think this is working. So just to make sure, and then we can create that in our loop. Okay, so obviously we need to have some metric, right? All right, and this doesn't actually seem to work that well. So, you know, we need to go back. Let's see. So maybe we can decrease the learning rate a little bit and see if that helps. Yeah, all right, so it's decreasing rather slowly, but nonetheless, we can see that it's decreasing. So it's 0.7, and yeah, we can see that it got to 0.3. Maybe it's a little bit too low of a learning rate. Maybe we'll do 3e minus 4, also known as the Karpati constant. And yeah, we'll use that. Hopefully it works. All right, remove that stuff. And what we need to do now is actually have a way of checking how good it is. So we'll go to utils file and we'll import pandas as PD, import numpy, import torch, and we're gonna do one get predictions. All right, so the metric we're going to use is ROC, and for that we're gonna need our target and then the predicted probabilities. So loader model, we'll send in a device as well. We'll specify first just model.eval for the batch norm. We'll do saved predictions, it's a list, and the true labels, also a list. We'll do with torch.nograd, right? We don't need to do unnecessary compute here. And then we'll just go through the loader for X, Y, and loader. We'll do send it to device, but we need to do small letters. Y.toDevice, and we'll compute the scores. So scores model of X, and then we'll do saved predictions plus equals scores, true labels plus equals Y, and then afterwards we'll toggle back the model training mode, and we'll just return the saved predictions and the true labels. You know, it would be easy to check in accuracy here also if you want. I'm just going to use that the ROC metric. So from utils we're going to import get predictions, and what we'll do is in between our training loop, so once per epoch, right? This data set is cheap to compute, right? It's just 200 features. So we'll do probabilities. True is get predictions. So we'll do this every epoch, validation loader, model, and then we'll do device equals device. Then we can do print f strings. We can do validation ROC, and that is going to be metrics.roc AUC score. First, we'll send in the true labels, and then we'll send in the probabilities. All right. I have, we'll just use that metric now, so we don't have to go into exactly how that works. Yeah, so I noticed one issue that we had right here is that in the scores, we need to also, convert that to a list. So we need to do toList, and similarly on the true labels. And hopefully that should work now. All right, so it seems to be working. We can see that our benchmark is now 85. I think we can get this up to 86 pretty easily by just changing some of the hyperparameters or just training more. But let's change the epochs to 15. We don't want to run forever. And yeah, so our benchmark is 85.2, which is not too, it's okay, but the score that we're gonna end up is around 92 in the end. So we can definitely do better. So how do we do better? Well, a lot of the things are just, what you could do now is just try different hyperparameters and try to improve the model that way. But I think getting some insight into the data and how that looks like, we can develop a better model by understanding the data a little bit more, which in this competition is, quite challenging because we don't know anything about the features. You don't have any domain knowledge of this at all. So what they were able to find out, I'm not gonna say it like I was able to come up with this because I read some of the discussions on the Kaggle competitions. But what they were able to find out is that, first of all, they looked at the features and were able to see that they were not correlated. So, that's not too difficult. We can just do train.correlation and maybe absolute value of that. And, if we do that, it'll take some second to run. But if we do that, we can see that the features are basically uncorrelated, which honestly doesn't make any sense. So you can imagine if you actually, collect data about if a customer made a transaction or not, that would be, the features would correlate in some way. But if we look at it, we can see that, there are very low values of all of these. And the conclusion was that the features are basically uncorrelated, and which is odd. But if we know that information, then maybe we can create some better neural network, right? So if we go back to a neural network, what's going on here is that obviously we're creating, all of these inputs, right? All of those 200 features. The idea of the neural network is to find some interesting pattern in those features. But we just concluded that there are no correlations. There's nothing there. So maybe we can use that information in some way to be able to create a more efficient neural network. And in fact, we can and we will. So what we will do is we can change our neural network. We'll just do self.fullyConnected1. And what this is going to do is it's going to take a single value, right? And take it to some hidden dimension. So let's do hidden dimension. And we'll also need, the batch norm that we had. So the initial batch norm on the input size. Okay. And then we'll do, let's see. So the second fully connected is going to be a linear of input size times hidden dimension to a single value. Right? Maybe this doesn't make too much sense yet, but the idea here is that since there are no correlations, maybe we can just sort of make every feature to its own example, right? And then we can reshape it back into that new example where each feature has gone through a linear layer and it has been mapped to some higher dimension. And so you can sort of view that each feature is going through an embedding, right, to create some better representation of that single floating value. And that also explains why can't we just use an embedding? Well, it's continuous data, so let's just use a linear layer instead. So for that, we'll first do x is self.batchNorm of x. And here's, I guess, the tricky part. We need to reshape everything to be its own example, right? Because now the shape of x, so current x shape is, let's see, it's batch size, comma 200, right? But what we want to do is x.view of -1, comma 1, right? So what this will do is it will create that each feature is its own example, meaning batch size times 200, comma 1, right? That's what we're doing. And then we can run that through our network. So x is self fully connected 1 of x. And then also use a relu on this. So maybe we can do, let's see, import torch.nn.functional as f. And then we can do f.relu. Is there no relu? Yeah, f.relu. Like that. And then we can just return self.fullyConnected2 of x. Or that's not correct. We need to also reshape it, right? So reshape of, all right, so let's do batch size in the beginning is x.shape of 0. And now we'll reshape it to be batch size, comma -1, all right? So we'll re-get the batch size, but now, of course, every single of those values has been mapped to a dimension of hidden dimension. So this will be, I guess, batch size, comma input size, so 200, and let's say the hidden dimension is 16, right? So 200 times 16. What is going on? So more generally, this is input size times hidden dimension. And now we'll just return it on the self fully connected of x, and we'll do torch.sigmoid of that, and then .view -1, same as we did before. So yeah, so all right, this might look a little bit complicated to do, but just remember that the insight is that the features are uncorrelated, so maybe we can use that information in some way. All right, so let's see if our experiment actually was worth it, and we'll now need to send in some hidden dimension as well, and let's use 16. Oh, sigmoid. All right, so it definitely seems to have, it was worth it. We can see now that we have 88.5, which is, okay, 88.6, almost 4% improvement just from that insight. And that is pretty amazing, right? So now we're even, doing even better. I think we can do a TQDM here. Just nice to have a progress bar. Or actually, maybe not. It goes so fast anyways. We don't have to have one. But okay, so we improved the bench line even further, and we haven't even touched the data, right? We haven't created any new features. So that is pretty amazing. And this would be it's an okay score already, but how can we make it even better? Well, for this, we actually need to do some more sort of feature engineering, but don't worry, it's not going to be anything really difficult. So the ideas here is that, all right, so there was sort of one key insight, or actually, let me just explain what we want to do. So, I think feature engineering is, I'm no expert at feature engineering. I'm totally new at it, in fact. But for me, at least, it seems that it's a very experimental process. So you just have some idea of what could be useful for the network. So you look at the data and you try to find out some information. And in this case, let's remove this. So in this, let's see if we can do it like that. So in this one, we can actually look, so let's just look at one single feature value in a single example. So let's take this one. what they were able to see is that this value is actually duplicated somewhere in the data, or actually sometimes multiple times in those examples for that feature. So, if we would scroll down, we would see this 8.9255 at maybe example, 1000 or something. So an idea is then that maybe if we know if the value is unique or not, maybe that gives us some information. So to the network, we could also say, here is 8.9255. That value is unique in the entire data set, right? Or if it's not unique, maybe that gives the network some extra information, or it doesn't give it some extra information, but maybe that information makes it a little bit easier for it to be able to distinguish what the actual target should be. All right. So, this idea is completely unsupervised, right? It's not dependent on any target. We are just looking at a single feature and just seeing if there's a duplicate. So we're not using the target information in any way. So then maybe we can also include the test set data to be able to have more data points of what is actually unique or not. Okay, so our idea now is that we can just look at each feature. We can include a test set as well. It's completely unsupervised. We can see if the value is unique or not, right? We can create a new feature at the end. Maybe we can call it var 0_unique, and we can set it to 0 or 1. Is it unique? 1. If not, 0. And since it's completely unsupervised, we can also include the test data in this to be able to get a better representation if it's unique or not. And here comes another sort of crucial information that they were able to find out, which was that the 50% of the test data was completely fake. All right, and I'm not sure why they did that, because then the test data is not representative. But anyways, 50% of the test data was fake. So if we use those values, then it's going to be a worse model. And also, so what was fake about it is that they just copied values. So they copied another row's value for that particular feature, and they just did that randomly, and there you go. That's a new example. But it's completely, fake. It's taken from the other examples. So our idea is to take out those unique examples, like those real samples from the test data, and then do our unique, check if the features are unique. And the unique ones of the test data are the ones that has a single unique value on from all of the 200 features. Okay, hope you're following with me so far. So we'll just do column names. We'll go through variable I for I in range of 200. Right, so we'll just do a list here to go through all of the variables, and then we'll go through them. So for column in tqdm of column names, and I'm not sure if I imported tqdm, so from tqdm import tqdm, and then we'll sort of do a count. Maybe we can just do 5 first of all. So we can do a count test of column dot value count, and maybe we can print count. So if we do that, let's do the import. All right, so what we get here is, so for variable 0, we can see that this value minus 3.66 had what was, there was a frequency of 8 for that one. All right, so that is, pretty interesting. And the idea is that we can now check which ones were unique, right? So we can do uniques is equal to count.index, where the count was 1, right? So we're checking index the values where the count was 1. So now if we print the uniques, we get a list of all the unique values. And now the idea is that we do that for the test set. So we'll do test column and we'll do a new feature on what is going on underscore unique, and then we can do test column and we can do is in uniques, right? So we'll take out the test column, we'll check, is it in uniques? And we'll set that to, this binary true or false result that we get here. So we can do that, and we can then just check test, maybe var 0 and then u. So here we get all of those 200 examples. We can see that, yeah, so this index 3 had a unique value for the first feature, right? So 0 or 1. Now, remember that while we're doing this is to take out the real samples from the test set, because we want to use those to get additional information. So we'll do test has unique. Then we'll do test of column plus underscore u for column in column names. And then at the end we'll do if there was any in axis 1, then we'll say that it has a unique one, right? So how we distinguish, how we take out the real samples is that at least one of them should have a unique value in any of the features. All right, so let's check if that works, and then has unique. All right, so now we have the ones that were unique, the unique examples. So maybe we can do .sum, and also here we need to change the column names to have all of the ones, and then now we'll do has sum. So here you can see that 100,000 of the examples were real, and then the rest were fake. Okay, so from that information we can now collect the real. So we'll do real test is test.locate, where we have test has unique. From those, we're going to take out the ID code, and we're also going to take out all of the column names, right? And then we can do pretty much the same thing for the fake test. So fake test. And this is just going to be where it doesn't have any, right? So not where it doesn't have unique. And I'm not really sure why all right, so now we can do train and test is pd.concat train and real test. Right, and if you're feeling lost, what we're doing here, we have just now collected so that we use the training data and the test data to get a better representation of the unique values. And that is, it feels a bit weird to do that. I don't normally like to even, touch the test set. But I guess it's okay because we can use that to just gain a little bit more information, and it's completely unsupervised as well. But let me know if you think this is sketchy to do. All right, so now that we've concatenated those, we can go through for column in TQDM of column names, right? So what we want to do now is map on that data set, see if it was unique, then we want to set it to 1. If it wasn't, then we're going to set it to 0. So we can just do a count. We can do train and test of column dot value counts, and then to dictionary, right? So maybe if we can just see how that looks like for one of them. So print count, right? So we can see here, this one frequency of 12, this one frequency of 12, right? So, it's obviously unique if it has a frequency of 1. So we'll do train and test. And we'll take out info. Or we'll add one info. Maybe we should call this something else. Maybe call it unique or something. And then we can do train and test of column dot apply. So we can apply a lambda function on this. So we'll take that value from that column, each feature. We'll do 1 if the count of x is equal to 1. Otherwise, we'll set it to 0, right? And then we're going to do dot values. Right, like that. So what we did now is we applied each value of those, and we mapped it to a new column, which is going to be 1 if the count was 1. Otherwise, it's going to be 0. And, you know, we obviously want to do the same for the fake examples. And this is pretty easy. We'll just do fake test of column underscore unique. And we're just going to set this to 0. And the reason why we're setting it to 0 is because, you know, obviously they were fake because they didn't have any unique value. So by sort of that assumption, it's not going to have any unique values. Okay, so that's it, right? Not that difficult, I'd say. And we just created 200 additional features. Very simple, it's just 0 or 1 if it's unique. And we did a little trick where we used the test data, and the test data had fake samples, so we just excluded those, right? So I guess, you know, this code right here, these two blocks, all this is just to take out the real samples. And all we did was this one, right? That's, if you look at what they did on the Kaggle competition, I can guarantee it was more complicated than this. But we're still going to get pretty good performance. All right, so what we're doing is we're taking out train and test. We'll take out the ones that were, you know, the test has the ID code to be test, right? That's the one that separates them. So we're going to do train and test. We're going to take out the column where it has ID code, right? That says train or test. We'll check .string .contains test. Then we know that it was a real test set. We'll do .copy of that data frame. So now we have a real test data frame. And then we can do real test .drop target. So the reason why we're doing this, maybe we can actually take a look at it. So real test. All right, so if we look at the train and test, we can look at, I don't know, 20 examples. We can see, maybe we need to show some more. So let's just do all of them. And we can see here that it has copied that target column. And it doesn't have any values there. So we have just set all of them to not a number. That's what pandas do automatically. So what we will do is we will just do real test.drop target, right? We don't have that information anyways, but we're going to drop it because it was copied when we concatenated those two. We're going to drop it from access 1 in place equals true. All right, so now we can do the same for the train, and that is going to be train and test. So pretty much the same thing, right? We're just going to copy this entire thing. We're just going to replace this test with train. Okay. So to get back the test set, we're just going to concatenate the real test and the fake test. Access equals 1. And that's it. So now we can do train.toCSV. We can maybe call it new shiny train.csv. Copy paste that thing, and we'll do test.toCSV. All right, and again, you know, we haven't really done anything difficult if you think about it. We just added, so maybe we can take a look at it. So train, what we did was just a single thing, which was to add, oh, now we only have a single one. We should have all of them. That's because we did this thing, right? Now we just have a single one, but we're going to rerun it and we're going to get all of them. But it's just a mapping. Was the variable 1, right? So the variable 1 here, this minus 6.7863, was this unique across all the examples? No, so we set it to 0. And this one was unique, so we set it to 1. Right? That's all we've done. So let's rerun this, restart and run all. And then hopefully if we have no errors. Okay, so now we can see that if we take a look at this, we can see we have the target, all the variables, and all of the new features, right? So they're ... but we have all of them up to 199 starting from 0. So we have 200 additional features, which is 0 and 1. All right, so what do we want to do now? What do we want to change? Well, first we need to go to the data set, right? We need to have our new shiny train data set. And we need to have our new shiny test. So now that we have those new shiny ones, one thing we can do is we can change the input size, right? But it's going to be 400 now. But one thing that, so I guess the question now is, how should we change architecture, right? Because we had a single feature now, and we did that because there was no correlation between the features. But now, obviously, those new features we created obviously has a correlation, right? It's impacted by the value of that feature. So an idea could be that maybe we want to instead change this thing to 2, right? Have the binary value, is this feature unique or not, and send in the feature at the same time. So send in those 2 values. And maybe that can give us some additional information. So, what I want to do is I want to take out the, first of all, we need to send it through batch norm, right? So we want to send everything through batch norm. And I think that's okay. Yeah, we can send everything through batch norm. So we'll do original features. You could also imagine that you just want to send in the first 200 through batch norm. Yeah, you might try that, but we're just going to send everything through batch norm. I don't think it will matter too much. We'll do original features is x of all examples and then up to 200. And then we're going to do unsqueeze 2. All right. So we're taking out, this is going to be n for batch size. So n, comma 200, comma 1. Then we can get the new features. That's going to be x of all examples and then 200 and above. Again, we'll do unsqueeze of 2. This is going to be 200, 1. Now what we want to do is we want to concatenate those. So we'll do torch.cat of the original features and the new features. We'll do that across dimension 2, right? Across this dimension. Now what we have after this, we have n, comma 200, comma 2. Maybe I can remove these old ones, right? This is just confusing right now. So we can do like that. And let's just call this n. What the? N like that. All right. So now we have the batch size as n. Okay. Now what we want to do, so we concatenated those. We're just going to take away this view stuff. We're going to send it through our fully connected one. We're going to do the relu, and then we're going to reshape it to be n, comma, -1, right? That's still similar, right? It's just that we have 2 ones that we send in through the linear layer. So what we'll have here is n, comma, 200 times hidden dimension. Same thing as before, right? There's nothing that has changed there. So actually this has to change, right? So we're going to do, maybe we can do input size of divided by 2. It's just going to be 200 though. So this is going to be 200 times the hidden dimension. And yeah, so that hopefully should work. I'm just trying to think if there's something else. Maybe, so the hyperparameters that I found that were pretty good was 1e minus 3 or 2e minus 3. So we can use that. And the hidden dimension, maybe now that when we have this additional information, you want to increase the hidden dimension. It's just a hyperparameter. I think 16 will still work pretty well, but let's just create a hidden dimension of 100 because we can. So why not? And hopefully this should work now. Obviously won't because it's the first run. There's always some errors on the first run, guaranteed. But maybe if we're lucky. Obviously, something didn't work. Should contain 401 elements. I wonder why that is. If we go back to the training data, maybe we can do train.head of 5 and we can see. So we have 402. So we have 1 for the target, right? We have 1 for the train ID. So this looks good. We should have 400 for that. And the test, I'm not sure why we have, here we have 401 because we don't have a target. That makes sense. So I wonder what's wrong. I think I know what the error was. So, you know, when we do this to a CSV file, we also obtain an index, right? This annoying index right here. We obviously don't want to export that as well. So we need to send index to false. Now we need to rerun this stuff, unfortunately, and we can go back. And I'll just wait for this to finish and then we can rerun it. Okay, so hopefully now there's no more errors and this should train. And while it is running, maybe we can start working with the other thing we're going to do. So we're going to do a new file, get submission. Oh my God, that is nice. See, that information was definitely good, right? It's just increased from 90 to 90 or 50 to 90 instantly, right? So those new features were definitely, valuable to the model. Yeah. So, I think what I had when I trained it, I got, or actually on the public leaderboard, I got, I guess on the private leaderboard, I got 90, just over 92. So I think it was almost 92.1. And the winners had 92.27. And I didn't do any model ensemble and I didn't add any more features. So, now we can see also that maybe we could have trained this a little bit longer, but we'll train for it's good enough. But anyways, I think that if you train model ensemble, you would probably get a slightly increase, and then if you added some more information, then you could probably do a little bit better, and maybe even take top 10 or something. So that would be pretty cool. But anyways, we'll do model loader test IDs, and then we'll send in some device. So we'll do all predictions is just empty from the beginning, model.eval with torch.nograd. Then we'll do for xy in loader and x.toDevice, nothing special here. We'll also x.toDevice, score is model of x. The prediction, all preds is going to be, the prediction, we're going to do score.float. I'm not really sure why I did that. I don't think you need to do that, but we'll do it. All right, and then plus equals prediction to list. All right, then when we're done with that, we've got all of the ones. We'll do model.train again, and we'll do data frame is pd.dataframe, and then we'll send in, let's see, a dictionary, and the first one we're going to have is ID code, test IDs.values, target NP array of all predictions, and that's is good enough. So then we'll do df.toCSV. So we got the ID code, that's the first column. The targets are the second one, which is all the predictions. And here we're not going to convert it to binary. We just send in the prediction because it's going to compute an ROC curve, ROC score. So we'll do sub.csv, and then we'll set index to false. All right, so that's the get submission, right? So at the end, after training, we can do from utils import get submission, and we'll do get submission of model test loader test IDs and device. Okay, maybe one thing we can change now as well is, since we saw that it was working, right? As our final submission, let's use some more of the training data. So maybe we can use just 1% to validation, or preferably 0. Maybe we can do 0.001, right? So pretty much all of the data for training. We can train it for maybe 20 epochs instead of 15, just to get that additional thing. And we can run this now. Pretty excited. Let's see what this gives us, and then we'll send this as our prediction. Okay, it didn't work. There was something wrong with the submission thing here. So maybe we can just copy that and put it at the top and see what's going on here. Maybe we can go to this and we can print x.shape. And I wonder what could be wrong here. In the test, we have 401 columns and we remove the ID code. And then we should have, and we're doing index equals false. So this should be all right. On the data set, we're loading new shiny test and we're also dropping that one. So how does this one have 401? Okay, god damn it. So here we need to do test data. Yeah, not training data. And that is why you should not copy code, ladies and gentlemen. Let's rerun this now, and I'll just wait for 20 more epochs. Okay, it is done. So we get our submission file right there. Oh, yeah, we can look at it. So we have probabilities right there. And that is good enough. So now let's go to Chrome, my submissions. So I got 92 point almost 1. Let's see if this gets as good. So late submission, and we'll just drag that over. All right, make submission. Hopefully we get pretty good. Come on, come on, come on. Hey, 92, baby. So that is really nice. And let's see, you know, if on the leaderboard, the private leaderboard, we can see there was 8,700 teams or people that made a submission for this. And from my understanding, that's the most popular one on Kaggle. And as we can see, 92 is right there, so 74. So we would have the 75th place, I guess. And yeah, I mean, this was 2 years ago, but we didn't do anything that had, you know, we didn't use a transformer or anything like that. We just used a normal neural network. All right. That is it. Thank you so much for watching the video. Hopefully this was useful to you. And if you want to see more Kaggles, I'll definitely make more Kaggle videos because I think this is pretty fun. All right. Hopefully I'll see you in the next video. Take care.